the people. In particular, in parts of this tutorial, I will closely follow the excellent survey of Ray, Schmidt, and Marley. When I have blatantly copied stuff, you can see it because I will make the header purple. But I recommend you check this out for sure. High-level overview, I'm going to start by talking about ballot types. How do voters express their preferences in participatory budgeting? We're going to see the greedy method. We will see why it's bad. Then we will see the good method, method of equal shares. And then talk briefly about some other rules. Okay, so what is participatory budgeting? Participatory budgeting is used by many cities to let their residents vote over how to spend a part of their budget. And so typically, and this is the case we're going to look at, these are particular proposals that come with the price tag, and we can either fully fund them, or not at all. And there's some given budget that has been set aside for that. And this way of doing participatory budgeting has been pretty popular. There is a Wikipedia article that I mostly wrote called List of Participatory Budgeting Votes that has a list of many of the major cities, above 100,000 people that used it. And here are some European ones. We can see some interesting patterns. Germany doesn't do it. There's Wuppertal here, but it's kind of fake because this is not government money. This was non-profit money. France does do it a lot, as does Poland. In Poland, I believe all major cities have to, by law, spend at least 0.5% of their budget via participatory budgeting. People say participatory budgeting comes from South America, and particularly Brazil. This is true, the idea, but this voting-based version of PB, I'm not aware of having been done there very much. So there it's much more participatory in the sense that we go to meetings together and then we discuss and come up with ways that budgeting should work in our city, whereas here it's sort of much more formal. Okay, and so these cities, many of them differ in how they let people vote over those projects. And let's just go through several standard ballot types that are used. The most general one, in a sense, that is used, I'm not even sure if this is used in this general form, is where there's a list of projects and you can just say a number, utility number that you have for that project. Is it used? Anyone know?
Yes. In Pruszków, from 1 to 10.
In Pruszków from 1 to 10?
Yeah.
Oh, that's nice. And 0?
Yes, and 0.
That's good. Yeah, so some cities are working with researchers and then they force them to use proper input formats. And then you might often assume that these are really utility numbers and that people would like to maximize the sum of those numbers. But the most common way is to use approval voting. Approval voting just means we have a bunch of checkboxes and the voter can choose which projects they like. Now, and most cities will put limits on how many projects you can approve. Some cities even give lower bounds. So either you abstain, or if you come and vote on the website, you have to vote for at least 3 projects, for example. And this is to prevent people from, their friend has proposed some project and I always want to go and vote for that. So I have to actually read the list of projects. Now, approval has the advantage of being simpler to use. You don't have to think, do I like it 51 or 52 much? But there is some ambiguity in how to interpret this. Right? If I select this butterfly park and the other things that this person here voted for are not selected, is that better for that person compared to this installing this one camera? And we don't know, we have no preference intensity information. An input format that's particularly popular in Spain is knapsack voting. In knapsack voting, it's a special case of approval voting where the projects that you vote for in total should cost at most the budget. So typically you will have some kind of bar shown in the voting interface that shows how much does the things you voted for cost so far, and then you cannot go above.
I'm not sure, but I think Barcelona used this, but you could do up to 1.5 times.
1.5 times.
Not sure.
Okay.
Also, I don't know if you took that into account in the map, but Barcelona only allocates 1% of the city budget to PP.
Yeah, so I'm not taking into account the percentage at all. Just do they do it?
Is what I mean. It's just.
It's not much money.
It's not a lot of money.
Yeah, but it's okay. But I think in Barcelona or Madrid, one of them had like quite a lot of money in absolute terms and very few voters. So if you divide the money by the number of voters, it was 3,000 euros per person. So you have, in a way, quite a lot of influence compared to other elections that one partakes in.
Roberto used this to renovate the school of his son. So he figured out that no one votes in Toulouse PP. So he did a personal project for the school of his.
Exactly. This is how one should do it. There's some public component to it. So what do we think of knapsack voting? There's actually been surprisingly little work done on it in academia. I think it's probably a bad format to use because we don't, for example, suppose there are lots of very big projects and only one of those big projects fits into the knapsack and then a couple of small projects after that. Then you can only tell me what's your favorite of the big projects. You cannot tell me anything more. And often people will try to fill up the bar or might even be forced to fill up the bar, and then they put lots of trash small projects in there, etc. So, and it's quite a lot of work also. Maybe you don't like enough projects to fill up a big part. But I think politicians like it because they want the voters to internalize the budget constraints, see that you cannot do everything. It's also cumulative ballots, which is a bit similar to cardinal ones, but there's an upper limit on what the number of points that you give out can sum up to. This is also used in several cities. The typical limit would be 10 points that you can distribute among projects. Ordinal ballots, which might be rankings or weak orders over the projects, typically truncated. So maybe, for example, you're only allowed to rank 3 projects. That's, I think, the input method in Krakow. Okay, so which of these is the best one? It's unclear. One thing you can do is you can ask actual voters what they think of these input methods, and that's what we tried to do in a little experiment in Zurich with 180 students from Zurich universities. These were excellent participants. So whenever we gave, it was like a long survey, but whenever we gave them the opportunity to explain their reasoning, like a free text input form, we would get like a lot of well-reasoned text. This is pre-LLM. So I was very impressed with that. And so what did we have them do? We had them vote 6 times in the same fake election. The fake election was made in analogy to the previous Zurich election. So the projects typically had some analog there. And what were the formats? First was approval vote. Select as many projects as you like. Select up to 5 projects. Distribute 5 points across the projects. Distribute 10 points across the projects. Rank up to 5 projects, exactly 5. And select 5 projects and then distribute 10 points across those 5 projects. And so a few disclaimers: everyone used these voting methods in the order I just mentioned. I now regret that choice because it means that voters learn as they go along and find things easier and easier because they now know the projects. The reasoning was that it's kind of a bit pedagogical to go in that order. But yeah, and also to make their lives easier, these 5 projects that we showed them to distribute 10 points were exactly the 5 projects that they had ranked in the round earlier. These are caveats to keep in mind. But then we asked them, how difficult do you find using each of the voting input methods? They found it extremely easy to select any number of projects. I believe it was select at least 1 project. Then generally speaking, distributing points was seen as more difficult. Yeah, so the approval ones are clearly the easiest to ask people, but maybe easiness is not the only thing that counts. Maybe it's also which of the input methods capture your actual preferences for these projects. So are these input formats expressive enough? And then people really did not like select any number of projects. What they did like is ranking. Rankings clearly describe their preferences. Also select 5 and distribute 10 points clearly describes their preferences. It even describes them, among people who say clearly, it describes them, more of them clearly than the strictly more expressive distribute 10 points across more than 5. So I suppose maybe it's less expressive. I don't know. I'll let you think about whether there's something that's lost. Right, and then we also asked them, what voting input method would you recommend a city to use in a participatory budget? And these are the border scores, reverse border scores, so lower is better, so it's average rank. And people really like the ranking, as you might have guessed from previous slides, and they really hate selecting any number of projects. So that's interesting. Why do people hate that so much? It's unclear to me. When I took the survey myself, it was to beta test. I also didn't like doing it because you never know when you're finished and you don't know what the question is really asking. Am I supposed to just give the very best one, so everything that's acceptable? And it's also the first time you really see the projects and have to think about them. Yeah.
Sorry, Dominic, to interrupt, but why did you choose 10 points?
Instead of?
I would say 15 points allow you to rank.
Right.
So why 10? And why 5?
That's right. Well, these, like 10 is a number of points that's in actual use. I agree that in this one, 15 points would have been more reasonable. We did ask them, how many points would you want? And people chose really large numbers. So quite a lot of people thought 100 points would be a better idea. Though I didn't make them do it, so maybe if they had to do it, they would be like, oh, this takes ages. We don't know. So I think this is worth redoing, essentially, this experiment, especially with non-Swiss people, which might be more representative of, like, I don't think they are representative of other nationalities. Right? Okay, here we see our first purple slide, where I've just hitting you with their list of all papers categorized by ballot type that they use. And we can see a certain bias towards working on approvals. And you will see that bias again very soon, because I'm essentially only going to talk about approvals. There's a little bit of work, but clearly this is an opportunity to study more. Okay, so let's set up a formal model. What is the model? We have a set of projects. Each project comes with a cost. We have a set of voters, and each of the voters gives us a ballot AI, and that gives us a profile of ballots. Then we have a total budget available, and an outcome is just a set of winning projects whose cost is at most the budget. Now some notes, suppose every project costs exactly 1 unit and the budget is an integer. And this problem is just a committee selection problem. Select K out of M candidates. And committee elections have been well studied. So there's a lot of literature on this. And so one can try to get concepts and rules and methods from that literature and then try to generalize them from this cardinality constraint to a knapsack constraint and see what happens. And I'll use this notation here. Cost of a set of projects is just the total cost of the projects in that set. Okay, so now let me introduce you to what most cities do once they get their ballot data. And so let's consider approval ballots for now. So this AI, the ballot that we get, is the set of approved projects of voter I. And so almost all cities that use PB, it's the same voting method. It's just really, it just sorts the projects by vote count and then takes projects if they fit. Right, so while we haven't looked for the projects, we take a project with the most votes, maximizing the number of people who voted for it. If it's possible to put this project into our knapsack without overshooting the budget, then we do so and repeat. This is essentially everywhere this is used. Some cities do not skip. So they have like an else break in here. So once they come to the first project that they cannot fit, they stop. But this leaves a lot of money on the table. Paris does something completely different, where you grade projects and then they take the median. But generally this is, so I have a quiz question for you. Clearly this procedure is trying to maximize something. What is it trying to maximize?
So each voter has a utility for each of the projects, and they want to maximize the sum of the utilities of the voters.
Right, so I'm using approval ballots. So the only input I have is the set of approved candidates. And so I've written some options here. Maybe this thing is trying to maximize the total number of approved winning projects. Or it's maximizing the total cost of approved winning projects summed over voters. Or maybe it's maximizing the total cost efficiency of the voters. Who thinks it's 1? Okay, so some people half put their hand up. Who thinks it's 2? A couple more. Who thinks it's 3? Okay, good. So we have full support. So this is a trick question because we have like this quantity, like the approval score over here, and this kind of look the same, but actually the answer is the sum of costs is what it's trying to maximize. And let me show you why. Right, we call the knapsack problem. This is, we have a list of items with payoffs. I've overloaded P now, so these are now values and costs, and available budget B. And we want to maximize the total value of our knapsack. What is the greedy algorithm for this problem? Well, it's the algorithm that proceeds in bank per buck order. So it takes the item that gets you the most per unit of weight used up. Right, and so we need this value here to be the vote count of the project. And for that, we need to go in order of cost. Vote count times cost of that project. Right, and so the greedy method approximately solves a knapsack problem with these payoffs, so it approximately maximizes this quantity, the total over the voters of the cost of the projects that they approve. Okay, So based on this, one can now argue that cities implicitly assume that this is what voters want, or that this is their assumption for how they interpret approval ballots. They think that if I approved some expensive projects and those were winners, then I'm very happy. That makes sense. But one could also use cardinality utilities, where I'm happier if more of my winning projects are winners. Okay, let's formalize this notion a little bit more. This of different types of utility functions, and this has been done using the concept of satisfaction functions. So, what are satisfaction functions? They take as input a set of projects, and then tell you how satisfied someone is with that set of projects. We assume how satisfied someone is with that set of projects, and we just put as an assumption this is monotonic. And so the satisfaction to a particular voter of some outcome set W is just the satisfaction of the set W intersect my approval set. Right, and so with this notation, we can now define what we've seen before. The cost satisfaction is supposed to be cost satisfaction, the cardinality satisfaction, but you can define other notions of satisfaction functions. You can define a coverage one, which we in this field call Chamberlain-Courant satisfaction, where my satisfaction with a set of projects is 1 if it's non-empty, which translates to there is at least one project among the winners that I like and 0 otherwise. Or you can go fancier and because you might be unhappy with both of these, right? You might think that, well, if a project is 10 times as expensive as another is selected, probably I'm not 10 times as happy. If you've ever voted yourself for a participatory budget, I don't think that's your experience. If you vote for, something that costs several million and something that only costs 10,000, but is, for example, immediately good for you, is like it's your children's school, right? Then probably you don't have like 100-fold difference in utility. But on the other hand, throwing away the size of the projects with the proxy of the cost completely and just going with cardinality is probably also not the right thing. And so this is why you might want to interpolate, for example, with the square root. Just as an aside, suppose a city were to actually use the cardinality satisfaction function and then, for example, do the greedy method. In other words, proceed in order of vote count divided by cost. It would be very simple in practice. It would just take the cheapest projects, essentially, because costs differ quite dramatically between projects, but vote counts do not differ very much. And so it is like the very least popular projects you don't take, but otherwise it's just the cheapest projects. That's usually not what cities want, especially cities. So cities differ a bit. So some cities, they just transfer the money to someone who is in charge of the project, might be a non-profit or something. But most cities actually follow or are in charge themselves for implementing the project. And so it actually comes with staff time and staff effort. And so they ideally do not want 150 winning projects. And so they need bigger projects. And this is a side effect of using cost utilities. And here is just one example that I'm going to skip. Okay, so we've seen the greedy method. All the cities use it. Is it a good method? And as you can see, there are more disadvantages than advantages. So to start with the advantages, it's certainly easy to understand for citizens, for government officials. Everyone can implement it. You don't need Python, you just need Excel and use the sort function. And we've seen it approximately maximizes a notion of utilitarian social welfare. So on average, your voters are going to be pretty happy. But there are also disadvantages because this method does not care at all that the happiness is evenly distributed across the population. And so in particular, many voters may be unrepresented. For many voters, it could be that none of their approved projects have been selected. The flip side, a large coordinated group of voters, they can get, in the worst case, all of the money. If you're a plurality, you don't even have to be a majority. You just have to be larger than other interest groups. And if you all come out and you all vote for the projects, then those will be the most popular projects and nothing else wins. So you can have 20% of the population getting 100% of the money. Because of that, cities do various hacks to make the method not as bad. So one of them is to do separate district elections. So you cut the city into pieces and then have each district hold their own election and you give them a proportional amount of money. Another one is that small projects have a pretty low chance of winning in practice with this rule, even if they have enough votes. Right? Suppose you have a small project, it gets per cost quite a lot of votes. Clearly there's enough support there for the project to make sense, but it's not the most votes. It's just a very large number of votes, but not among the most, so then you do not win. The method almost ignores the cost of projects. Often projects are proposed by citizens. And so like we'd like for them to limit the scope, maybe be cost effective in what they propose, but this doesn't matter. Only the vote count matters. The only reason why the cost asking for more money might hurt you is that you might overshoot the budget, overall budget limit. And there are, for a similar reason, there are incentives for project proposers to bundle their projects. So suppose you have two projects that you can merge, and then, for example, your voter sets might also merge as a union. So it doesn't add, because there might be intersection, but it still goes bigger. And so the project will still win, or you have a higher chance of winning, essentially at no risk. There's a lot of problems, and all of these problems we do see in cities occur from time to time. And it turns out that there's a single solution to all of those problems simultaneously. Dictatorship.
Council PB.
No, dictatorship is the wrong answer. It could leave many voters unrepresented. Okay.
It's just one.
And the answer is proportional representation. It's what most countries use to select their parliaments. The general idea. If a particular idea, a particular party has 30% of the votes, it should get 30% of the seats in parliament. Of course, unfortunately, we are currently here in a country that does not follow the sensible principle. Essentially, any election helps. And we can transfer this idea to participatory budgeting and to many areas of collective decision making, where the idea is if you have 30% of the population with particular interest, then we should spend roughly 30% of our money on projects of that type. But how to formalize this idea? It's not so easy. Turns out the most productive ways, or no, a productive way is by writing down representation axioms, which are group fairness axioms. In particular, there is EJR, which stands for Extended Justified Representation. And this has been proposed initially in the committee elections literature. And there are precursors in the literature on STV, which is based on rankings. Okay, so an outcome satisfies EJR if for all groups of voters, every proposal they might make, so proposal is a set of projects, and it's not too many projects. So the group is supposed to be able to afford their proposal with their fraction of the money. Right? So the cost of those projects that they propose needs to be at most the budget times their share. So if it's 30% of the population, they must come up with a proposal that costs only 30% of the money. And this proposal is supposed to be such that they all agree that this is good stuff. Right? So everyone in the group needs to approve all of the things in the proposal. Then there should exist at least one voter in that group such that their utility, their cost utility, should be at least their cost utility with their proposal. So why does this make sense? I suppose this was not the case and an outcome would fail that, then we would have a group. They can point to something that they deserve in terms of budget share. They all agree it's good, but all of them like less than this stuff. Right? And in order to avoid the situation where all of them like this, the outcome less, we need to say there's at least one voter who likes it more. Okay, and so suppose we could somehow magically find an outcome that satisfies this property. You can already see that it will get rid of certain problems with the greedy rule. In particular, it will say that if there are, apologies. It will mean if we have a cohesive group of voters, cohesive meaning they have things in common, then they will not be unrepresented. And in particular, you cannot be overridden by a larger cohesive group. You get something. You can also see EJR as a guarantee for projects, for a project proposer. Suppose you propose the project and you're out there campaigning for your project. How many votes do you need? And generally, the answer is if you have enough single-minded supporters, people who only vote for your project, then you are guaranteed to win under any outcome that satisfies EJR. So if the project costs 20% of the budget, then you need 20% of the population to vote just for you. Okay, so what rules satisfy EJR? So as I say, a natural thing to try is to look at the committee literature and see what rules satisfy EJR. And the paper from 2015 that introduced this concept showed that the PAV rule satisfies EJR. So you could try that. The PAV rule is one that is a global optimization rule for an objective function that imposes a certain decreasing marginal returns to additional candidates that you like. But it turns out that PAV does not work at all if you move from cardinality constraint to a knapsack constraint. Okay, then you can look further in the literature, and there are actually other rules that satisfy EJR, such as the greedy justified candidate rule and the method of equal shares, and some others. And so you might hope that they work, but you will be able to find counterexamples for all of them. And the reason is that they are polynomial time, and you can easily see that unless P equals NP, there's no polynomial time method that produces an EJR outcome. And the reason is you just restrict attention to the n equals 1 case, one voter. So let's have a look at the definition again. So there's just one voter. Now we have a group of just that singleton voter. EJR requires that for every proposal that this one voter can afford, that is, fits into the knapsack, at least one of the voters in that singleton needs to like the outcome at least as much as the cost. So this is just a knapsack problem in disguise for a single voter. You need to be at least as good as the best thing you can do. And so we would need to solve knapsack or subset sum or something like that. I believe it is open, continues to be open, whether there's a pseudo polynomial time algorithm for this problem. right? Because of course, knapsack, etc., they have dynamic programming algorithms. And so you might hope that you can somehow do some dynamic program that works for this. I don't think anyone has succeeded at this. Okay, so polynomial time rules cannot do it, but it turns out it is actually always possible to do it. So on every instance, there exists an outcome that satisfies EJR, and there's an existence proof for that, but it is computationally totally intractable. But we've got the greedy cohesive rule, just starts with the empty set, then looks for someone who complains about it, the worst, puts their proposal into the committee, and then repeats. And you can check that this satisfies EJR. Okay. And by computationally intractable, I mean, if you actually try to implement this with an ILP solver on a real size instance, it will not do it, at least in my experience. I mean, I've only waited a few hours, but it's extremely hard. But luckily, we can actually get almost EJR using natural polynomial time methods, and in particular, the method of equal shares. So I'm going to give a definition of this method. This is restricted to only approvals with cost utilities. You can define the method of equal shares much more generally, and then it becomes more complicated. And this method has actually been used by several cities, and it has been used in this form. This is also how we explain the rule on the website. We have equalshares.net that explains to anyone who visits the website how to use the method in practice. Okay, so let me start with a sketch of the definition. And the big idea is that we assign each voter a virtual budget. Like the overall budget B, we divide it into n pieces and assign it to each voter. And the rule is going to be, I'm only allowed to use the money that I've assigned you for projects that you voted for. So that means no one else can use your money. And so if you're 30% of the people, you're assigned 30% of the money, and we use it for things that you like. So this is the main idea. So we start with an empty winner set. We compute the set of affordable projects. Affordable here means that the total amount of money held by your supporters must cover the cost of your project. If there are no such projects, we're done and we return. Otherwise, we select the affordable project that has the highest effective vote count. So I will define that later, but roughly it's your vote count. It's the number of votes, but we ignore voters that do not have any money left. And the reason is, if you have no money left, it means that you have already spent all of your money. We've already given you things that you like, and so you shouldn't influence later rounds. And then we deduct the cost of this project from the budgets of the voters for P star. And we will do this by spreading the cost as equally as possible among them. Okay, so let's see an example. So here we have 11 voters. We have a budget of $1,100. So the method will start with $100 for each voter. We have 5 candidate projects: a bike path, an outdoor gym, a new park, a new playground, and library for kids. These are not very large parks. And these are our approval profile. We can see that there's almost a partition in interest. So there seems to be a voting block here that is quite sporty, and another voting block here that enjoys things that you can do with kids, for instance. So these might be parents. What does the greedy method do? Well, it computes how many votes does each project get, and then starts with the most popular ones. And actually the top 2 exactly fit into the knapsack, and that's what we do. So this is what the greedy method does. And so probably not very good, because we have like this voting block here who's large enough to deserve something, but they get nothing. Okay, so what does the method of equal shares do? Oh, we begin by dividing it equally, the budget equally among voters. We start with the project with the highest effective vote count, which at this point is just the vote count. So this is going to be the bike path. We see there are 7 people, each with $100. That's just enough to be able to afford to cover this project. And so we do it and we take the money. Now, what's the new effective vote counts? They will have changed now because the outdoor gym is not affordable at all anymore. So all the supporters of that project have gone down to zero. They've spent all their money. So there are no voters left with more than, no supporters left with more than zero. So the effective vote count went to zero. It's not affordable anymore, so we skip it. But also the new park is reducing an effective vote count because 3 out of its 5 supporters are now at zero. So we don't count it anymore. So it has only 2 supporters left. But the new playground is now the most popular one, 200. We can divide it equally among its supporters. Each of them pays 50. We select it and take the money away. And then we can take the library for kids afterwards, take the money away, and that's the final outcome. And it seems more equitable. Okay, so this example was chosen that nothing bad happens. So everything is super nice, but we need to be more precise so that this method works for all the things. So I'll start by telling you what it means to spread cost as equally as possible. And it just means that we distribute it among the project supporters in a way to minimize the highest amount T that any of these voters contribute. And so we minimize the maximum amount. So here's an example project, costs $500. It's approved by all of these people. Okay, how many is this? Would be 10. Yeah, 10 people. So if we split it equally, it would cost 50 each. But suppose that these people here only have 20 left. So we cannot do it equally. It's going to minimize the maximum payment, which means that the poorer ones spend all their remaining budget. And then after this, we have 400 left, and this will be split among those voters. Okay, so in this case, this is the as equal as possible cost split for this example project. And we're going to remember this value T of the highest amount that anyone pays. And we will call these voters here full voters. The full voter contributes, votes in full for that project, contributes the correct amount, the full amount. And the other voters are fractional voters, and they will only count a fraction. In particular, these will only count a quarter. Okay. Now here's a nice inequality. If we add up T for all the full voters and the remaining budget for all the fractional voters, then we cover exactly the cost. That's just adding up all the dark blue parts. Okay. Now the effective vote count of a project is the number of full voters, plus for each fractional voters, the fraction of the full contribution that they get. So here we have 5 full voters, and these all pay a quarter of the full contribution, so they count a quarter of a point. And so this project has an effective vote count of 6.25. Okay, so why does this number make sense? To start with, in the simplest case, voters who have nothing left anymore, they do not count in the vote count. That's what I told you before. Voters who have a little bit left, they count a little bit in the vote count. That makes sense, nice and continuous. And also, from this equation here, we have T times the effective vote count equals the cost of the project. So what does this mean? Suppose I'm one of these full voters, and the method is going to take one of my dollars to purchase the project. And that project, that I actually get a multiplier of T, of the effective vote count. Right? So I give $1, but the total amount that gets given to the project is the effective vote count many dollars. So other people also give $1, and these all, because of cost utilities, accrues to me. So a kind of multiplier effect. And so what I just said is you take the cost of the project, you divide it by T. So this is how much utility I get per dollar as a full voter. That's equal to the effective vote count. And if I'm one of the fractional voters, it's even better for me because I pay so little for that project. Okay, so now that we know how it's defined, we can see a more complicated example. So this is the example as before, but now we're going to change it. So here an approval went from up here to down there. So now the outdoor gym is the most popular project. We begin here, we let people pay equally. And now the bike path is not affordable anymore. But now we have to compute the effective vote count of the new park. And if you equally spread the cost among those people, you get 2 full voters and 3 roughly 2/3 voters. This adds up to 4.13, which is more than 4 and 3. So we take that. And then we take the new playground with this effective vote count. And then we're done. Okay, so do you like this outcome? Is it good? Yeah.
Use all of the money, right?
Doesn't use all of the money, no. So we stopped here, but how much did we spend? We spent 600, 850 out of 1,100. There's quite a lot of money left over. Particularly, there's a lot of enough money left over, certainly to buy the library for kids. But the method of equal shares refuses to do it because those 3 people do not have 100 left over. Don't they? 40 plus 40 plus 40.
0 plus 39.
Okay, yes. Right, so the method of equal shares stops. And this is actually a generalized problem. I apologize for the slides. So let's look at the slide instead. Here, what I've shown you is, let's look at just this line. This is the percent of the money that MES spends on actual Warsaw instances in this case. Right, and so we see it spends in Warsaw 60 to 70% of the money and leaves 30 to 40% on the table. In other cities, it is worse. And so an idea you might have to make it spend more money is to just give out more money at the start. Right, so you give voters extra money at the start, and thereby we'll be able to afford more. Right, and in particular here, this is what I'm doing as we go right on the x-axis. I'm giving more and more money to the voters at the start, and then see how much it costs, how much the winning projects cost, right? And we see it crosses the 100% of the budget line over here. And so we need to give roughly 40% more budget to voters to be able to actually use the money. And so this is what it says on this slide. So MES does not usually use all the available money. In particular, it is not exhaustive, as we saw on the last slide. So there can be projects that still fit into the knapsack, but MES refuses to take it. And so people have worked on coming up with various completion methods. I apologize for the term, because you might think a completion method takes the outcome of MES and adds extra projects to it. But several of these options that I have on the slide do not necessarily do that. They might just elect a completely different set of candidates, but one that costs more. Okay, so the simplest one is just utilitarian completion. You do MES, and then you take the most popular projects that are left over till you run out of money. Perhaps a reasonable thing to do, but I mean, you use MES in the first place to be proportional. You probably want to use all the money fairly and not just 50 to 70%, but you can make both arguments. But the most common way is add one. What is that? We repeatedly increase the voter's initial endowment by 1 currency unit. So in our example, everyone had 100 at the start. That didn't lead to enough spending. So then we run it again with 101, 102, 103, etc. Now in Hungary, you don't use 1, you use 1,000. because the currency is worth much less. And so if you use one forint, then you have to wait a long time until it converges. So you see that there's a certain arbitrariness in this procedure. This is not scientifically determined as the right number. Right, so there are a couple of variants of this. A nice feature of this is that the final outcome at the end is an outcome produced by MES. Right? But I can just, if I have to explain the outcome, I can just tell you, well, the method begins by giving everyone $140 at the start, and then we do what I just showed you, and we come up with the final outcome. I don't have to say, well, first we do this complicated method, and then we use this other method, and then we use another. But unfortunately, this doesn't really fix the problem. It is still not necessarily exhaustive. So it could be that as you go up and up, at some point, the next increase would jump above the actually available budget, but you're still not exhaustive. There's still another little project that fits. And so you can do add one U instead. That stands for add one, and then do utilitarian completion after that. Yep.
Is it monotone if you increase it?
No, it is unfortunately not monotonic. We can in fact, I guess, see this on this graph, where if we give out more money, it could be less money that's spent. And the reason is that this is a sequential rule. So as I give out more money, something changes, and then everything after that changes in unpredictable ways. So it's really badly behaved. You cannot do a binary search. I mean, you can do it, but it doesn't really make sense. You just end up at a semi-random point. Add one U. So we talked to some people in the Netherlands, and they were against doing add one U. They thought that the U part is not motivated, it is not fair. In particular, it could be that there's a project with very few votes that doesn't have legitimate support, and then we still fit into the budget. And there's some recent work that tries to remove this 1 unit business or 1,000 unit business, but by sort of looking continuously at the amount of money we give. But that's quite a tricky thing. And so this paper actually has to redefine MES to be slightly different for it to work. Okay. Good. So what's good about this magic method? Why is it the right definition? It has a lot of arbitrary looking elements. And the answer is this: it satisfies EJR up to one project. All right, so we've already seen EJR. This is the same definition, except that we say that there must exist. So EJR just says the cost, my happiness needs to be at least the cost of our proposal, the happiness I would get from our proposal. Too hard to get for computational reasons, among others, but this holds if I give you one bonus project. So if there's some project in your proposal, but that wasn't winning, if I put this in, then I get above this amount that we deserve as a group. Okay? MES satisfies EJR 1.
Even does EJR X.
Up to any good, yes.
At least in this case.
In this case, that's right. Yeah, so you can say there exists INS such that for all projects P, and I have a proof on this slide. And I think actually establishes the any version. Okay, so let's see whether we can do it. So consider a coalition of S voters, and they have a proposal T. Okay, and so if all of T has been selected, then we are done. Okay, good. Otherwise, there is a P star that hasn't been selected, and so in fact, I'm not choosing a particular one, but any of them. Okay, so why was P star not selected? It must be that there wasn't enough money among its supporters to select it. It must have become unaffordable at some point. Okay, so in particular, the people in S do not have enough money at the end of the procedure to pay for P star. So in total, they have strictly less than cost of P star money left. And so on average, they have less than cost of P star divided by S left. Okay. So this is the first idea in the proof. It says in this EJR group, there's some voter who spend a lot of money, and spending money is the same thing as getting utility because money is spent on things I like. And now I just have to show that I've actually used that money in a good way that you like, and then you have lots of utility, and that's what we're trying to show. Okay, so there exists at least one person who has even less money left than this. So consider the first time when the budget of someone in S drops below this magic value. Let's call that person I, and note that I has now spent strictly more than the money he started with minus what he ends up with. Okay. Now note, up until this point in time, the group S could afford P star by themselves with equal cost split. Because until this time, they all have at least this here left. So we can equally split just among us. And so this means that the effective vote count of P star was always at least S. Like everyone in S is a full voter. So the effective vote count is at least S. And now we always pick the alternative with the highest vote count. So far, we've always picked projects with a higher vote count, weakly higher than S. Okay, so what we have is we have this person I who has spent a lot of money on projects with effective vote count at least S. Recall that for each dollar that I spends on such a project, a total of at least S dollars was spent on that project by all voters. That's this conversion factor. And therefore, what's my utility? What's the cost of the things I like in the outcome? Well, it's at least S times the money I paid equals this amount. And that's what we have to prove. Move this to the other side. And then it says this inequality. And so that's the reason that we are splitting costs equally and finding effective vote count. Okay, so as I mentioned, MES has been used by several European cities in the last 2-3 years. Liczka was the pioneer in Poland. It used MES for its Green Million PB, where they had 1 million zlotys to give over ecological projects. And what we found is that MES selected projects all across the area rather than just in the center. And if they had run the greedy method with the exact same votes, it would have been very center focused.
How about the add to one version of MES? So can you find an axiom that it satisfies, which is similar to EJR?
Okay, so EJR is satisfied by it.
Okay.
Because we are running, the outcome is just MES with a bigger number.
Mm-hmm.
And so if the number is bigger, everything that you were previously able to claim as a group, you are still able to claim. So this EJR is closed under increasing budgets.
I see. Okay.
So it's even better in a sense. Smaller groups get the guarantee.
Another question on can you make MES work if you don't have like additive, the idea that you get additive utility from additional cost, but like some marginal returns?
Yeah, so you can definitely define it because we've made some decisions already. And so now I just treat you as if your additive valuations have changed. I just always take your marginal utility for the next project in deciding what are the effective vote counts, etc. I don't know whether anyone has had any positive results on any of this? I mean, some constraints can be seen like that, right? So
we thought about it, and
no,
it doesn't work for non-additive.
doesn't work. Yeah.
So the greedy committee rule works for anything that's, I think, sub-additive or sub-modular. But for MES, we tried, and as far as I can tell, I don't think it,
Right.
at least for general sub-additive or so, it doesn't work.
Yeah. Yeah, no. But indeed, if you then put your sub-additive valuations, for example, and try to put it into the definition of EJR, then it's also not clear how you can make that definition of EJR work. Naive ways of doing it will give you an unsatisfiable axiom.
No, I think that's not true. Like, you can define EJR for any non-additive utility function, as I said, the greedy rule will still work in most cases.
But it doesn't satisfy EJR, the greedy rule.
No, the greedy cohesive.
Okay, yes, correct. Yeah, that's right.
At least for a sub-additive, I think.
Yes, no any monotone. Okay, more on this. I go on to the practical stuff. Okay, so I told you about Velichka. Let me show you Velichka. This is how it looks. And I've drawn a dot for each funded project according to the method of report. Yes, it's so cool. Usually what you do is you take something and then you simulate your new rule idea on it. But here we take our new rule idea and then we simulate what the normal thing would do. And so this is what the normal thing would do. And you can see there's a lot more concentration of the winning projects in this central area, and these outlying villages here do not get anything, whereas MES spreads the money out more equally. Now, of course, this all needs to be caveated, because if you use the standard greedy voting method, people would vote differently, almost certainly. And there's, for example, there's a city in Aarau in Switzerland that used MES in a pretty small prototype way. It also selected projects all across the city, but there were like several workshops of people who were thinking of proposing projects, and they were very interested in how exactly does MES work and what are the incentives facing us as project proposers. And we essentially told them, if you give us a smaller project, you're more likely to win, because it's easier for you to get the required number of voters. Okay, so here's how the outcome looks in a tabular form, where I've sorted the projects by the vote count. You can see that here we skipped a project, even though it had a lot more votes than the one afterward. We skip it and do not fund it because it is pretty expensive. And it turns out the people who voted for project number 21, many of them also voted for project 6, which was already expensive. And so this is why we skip it. And a similar story here for project 16. And we tried to visualize the outcome. I'm not sure exactly how successful this attempt is. What this shows, especially in this compressed way, up here it shows the amount of money that the project costs, and then the length of the green bar is the amount of money that the supporters of that project have, right? And so the green bit is hopefully longer than the cost, so that you can afford the project, right? But there are some red parts, and the red parts is money that you've spent in previous rounds already. And so here you can see there's this large red area, and that corresponds to spending by the supporters of project 21 on project 6. This is why it wasn't selected. And after the spending, the amount of money they have left over is strictly less than the budget. All right, so this is method of equal shares. Are there other good voting rules? Opinions differ. Here's one, sequential Fragmain rule. This is after a rule proposed by Edward Fragmain in 1894 in the context of electoral reform that was going on in Sweden, and for some reason he wrote that paper in French. And so it's not too dissimilar in a way from method of equal shares. It also uses the idea of giving money to the voters. But it does it a bit differently. So in MES, we give the money up front and then we use it. And in Fragmain, we give it continuously over time. Okay, so voters now start with a budget of 0, not B over N. And voters continuously receive money as time passes. And so at time t, a voter has received t units of money. And so at some time t, we let PT star be the set of projects for which the supporters of that project now have enough money to cover its cost. This is again supposed to be cost. As soon as we reach a point t where this set is non-empty, so some supporters can afford a project, we take it. If we can afford it. If we cannot afford that project, we stop. But otherwise, we take a project from the set, take the money away from those supporters, so they go down to 0, and resume the process. Okay, so this is the way the method has been defined by these authors, and this weird stopping condition here is apparently required to get priceability to work. Okay, let me give you an example of how this method works. Here's a small example. We have a budget of 10, and we begin, time runs, and these bars continuously fill over time. At time 4/3 of a second, we have given each person 4/3 of a unit of money, but there's this project 1, whose 3 supporters therefore now have 4 units of money, which is enough to pay for its cost. And so time stops briefly at 4/3, and we take the money away from all those supporters. I don't know, why do people go missing? Oh no. And then time starts again, and after a while, P2, supporters of P2 have accumulated enough money to select it, and so on. Maybe there's something wrong with the text, not sure.
Projects go when they're funded.
Second?
The projects go when they're funded, right?
Yes. Oh, I see.
For projects rather than voters.
I see. Great. Thank you. Yes. That's right.
Yeah, that's right.
And then P5 gets funded, but is in fact too expensive to put into our bundle, and then we stop. Okay. So one nice feature of this rule is that should the city decide later on, actually we have more money that we want to spend on our PB, you can just restart the rule where it left off and continue until you selected a few more projects. This is a property known as committee monotonicity. This would be failed by method of equal shares in general. So is the Fragmain rule a good rule? So it violates the EJR property. And so we cannot say it's a good rule in that way, but we can say it in a weaker way. It satisfies a weaker version of EJR, which is called PJR. And so let me first go through the motions of defining EJR X with respect to a given satisfaction function, which is now a bit more general, which says that for all groups, their proposals, they all like everything in the proposal and they can afford that proposal. Then there should be some voter in it, such that for all extra projects, at least with that project, that voter gets enough utility. pi here is supposed to be the outcome. And PJR is different. PJR says that the group as a whole, in a sense, gets enough satisfaction. It's not necessarily any particular voter in the method, but if we take the union of all the projects that these voters like, we spend enough money on that union. Okay. Maybe this is a bit fast to really comprehend, but I'll continue. Here's just a little example to illustrate the difference between the two methods. Suppose we have K voters, and suppose they have enough money to afford K candidates. These candidates all cost 1 unit. Right, so there are 2 possible outcomes. I could take all the blue candidates, or I can take all the green candidates. Both of those selections satisfy PJR, because in both cases, I select K candidates from the union of all the things they approve. So here, to read this as here's a voter and they approve everything above them. But clearly this is the bad outcome. You don't want to take the blue ones, you want to take the green candidates that everyone approves. But PJR is too weak to demand that. But EJR is strong enough to say at least blue is bad. You have to take some green candidates. Okay, and so here's a result obtained in this nice paper. So it does essentially the proof that we just saw. It generalized to show that MES defined for a given satisfaction function, so either cost utilities or cardinality utilities or what have you, satisfies EJR with respect to that satisfaction function. And then they show that sequential fragment satisfies PJR with respect to any satisfaction function, almost any satisfaction function. This is a bit surprising. So first note that the definition of fragment does not require to know any satisfaction function. But yet it still satisfies as PJRX for all so-called DNF, decreasing normalized satisfaction functions, which includes cost utilities, cardinality utilities, square root utilities, etc. All of them simultaneously. So you don't have to tell fragment very much, but it's good on all these criteria simultaneously. Don't know what to take from this. Probably the answer is that the axiom is too weak. If you're able to make people happy according to such extremely different criteria. So I think overall, probably sequential fragment has been understudied for PB, because it is simpler for sure to understand than method of equal shares. Okay, how much time? So now we had EJR, and we weakened it. We can also go the other way. We can try to strengthen it. And there is a strengthening called the core. The core, it's very similar to before. Again, we have a group S. Again, we have a proposal of that group S. Again, that proposal needs to be affordable with the money of the group S, but T is not necessarily unanimously approved by everyone in S. So now we allow there to be some disagreement within the group, and we're still going to give you a guarantee. The guarantee is supposed to be that there exists at least one person among S, such that their utility with the outcome is at least T. I'm sorry, I copy-pasted this and did not correctly replace the notation. ChatGPT didn't spot. Okay, open problem. Does there always exist a core outcome for the cardinality satisfaction function? This is essentially the question that's well known in approval-based committee voting, where the core is not known to exist or not exist, but that is even true for when you move to knapsack constraints to PB, which is really interesting. For example, in the committee context, PAV gets very close to satisfying the core, but it completely breaks under knapsack constraints. So probably the core becomes significantly harder, but we still have no counterexample. However, if we do cost utilities, then there exist examples where the core does not exist. Even pretty simple examples. And generally these examples are cycles. This includes this example. You can also write down, if you allow yourself general additive utilities, you can essentially do a Condorcet cycle. And then the core condition will essentially say you need to satisfy majorities, and you cannot satisfy all majorities simultaneously. Okay, and so now we have something that we cannot always satisfy. And there are computer scientists, theoretical computer scientists in the community. So what gets done is that the approximation factors get determined. There are at least two ways of approximating the core, finding outcomes that are in the approximate core. One of them is, I didn't want to write down the formal definitions. One is alpha satisfaction approximate core, which says there shouldn't be a collection S and T, that everyone prefers T a lot to the outcome W by at least an alpha factor. So for example, alpha equals 2 would mean there's a group who can come up with something that doubles each of their utility. And you can actually prove that MES satisfies an approximate core notion, where this is the approximation factor, closing parenthesis. It's logarithmic in something that depends essentially on the budget. How big is the budget? Or you can get an outcome with a constant factor approximation, 9.27 approximate core. The way to get there is you take a so-called Lindahl equilibrium, that's a fractional solution, and you round it randomly. And there's this other approximate core notion, that's the alpha endowment approximate core. And here we instead approximate not the utility improvement, but the size of the set T you're allowed to give. So for example, for alpha 2, now you're only allowed to use half of the money that you really deserve as the group, right? So you only get really small proposals, and I only have to make you happy with respect to that smaller set. And their existence is known for alpha equals 32, and then a recent improvement to 6.24.
Do you know what's the algorithm there?
Yeah, so it's called Lindahl equilibrium with ordinal preferences, and it's very odd concept. So you'll have to look at it. It exists by fixed point argument, but you can compute it and then you round it again, I believe. Yeah. You can compute something similar to it in polynomial time at the cost of a bit, and the approximation factor goes up to maybe 13 or 9, I forget.
So that's not polynomial, right? 6.24 is not polynomial. In polynomial
that's not polynomial time, yeah, that's existence. Yes. And the 32, it's only arguably polynomials, randomized maybe, but it's also pretty ugly. But both of these results hold in much more general models. Additivity is not required. You can generalize the knapsack constraint to more.
Does it work also for rankings, kind of like?
It does. Then you get the local stability notion.
Yeah, exactly.
And for that, actually, this 32 improves to 16 because you only have sets T of size 1 essentially. But that 16 has also been brought down twice. Once by the famous paper, 6 candidates suffice to gain a majority. And then also by these two, I think, with the third person, again, via Lindahl equilibrium get further down. I think it's in the fours, but don't quote me on that.
So that's in the last paper, right? Also.
No, it's two separate papers. Okay, and so I've only defined very few notions, even if it might feel different. There are way more notions you can define. This is taken from the survey, which you can see from the purple. There at the top in red, we have properties that cannot always be satisfied, and then the rest can always be satisfied. And as we go further and further down, they can even be satisfied in polynomial time. Okay, so all those things we've seen, is it good? Do we have the best possible method now? Maybe, or maybe not. So there's something that has been termed by these people the Helenka paradox. And Helenka is a district in Zabrze, Polish city. And in their 2020 elections, there were not very many projects in Helenka at that time. Project A and Project B. Project A was very expensive, $310,000 or some other currency. Project B, $6,000. But this project also only had very few voters. Okay, so what should we take? What should be the outcome? The budget is 310,000, so exactly what Project A costs. And now the problem is, if you take 11 voters and divide it by 414, the total number of voters, and then multiply it by 310,000, you get the amount of money that these 11 voters deserve, and it is 8,000. It's more than 6,000. So if you want to satisfy EJR, you must take Project B. After you've taken Project B, you cannot take Project A anymore. So your voting rule will stop there. Now, technically speaking, method of equal shares doesn't satisfy EJR, it only satisfies EJR1 or EJRx. So it could get around it in principle, but if you run it on these numbers, it selects Project B and then finishes. So arguably, this is not right. It doesn't feel right. The majority is so big that surely we should take this much more efficient project. We should make 400 people, 403 people happy rather than just 11 people happy and throw away lots of money. So if this troubles you a lot, then you probably have to abandon EJR. And once you have abandoned EJR, probably your design space opens up a lot, but it includes in particular what's been termed the bounded overspending MES or BOSS, which allows voters to spend more than they have. Essentially, this is the bounded overspending part, but only if the thing that they're spending money on is particularly efficient. And this means that Project A here would win, even though technically they cannot afford the project. Okay, so I just wanted to plug a recent paper of mine that I'm very excited about Lindahl equilibrium. So what we've been talking about is an indivisible setting where you either fully fund a project or do not fund it at all, but you can also define a fractional version of this thing, right? So a fractional version, then the outcome is a map little x that tells us for each project, how much money do we spend on that project, right? The amount of money we can spend on project P is at most the cost of that project. So there's an upper limit to how big you can make your park or whatever. And we only can spend the budget B in total. Right, and so it turns out that if we allow ourselves fractions, then the core always exists. The core always exists thanks to something called Lindahl equilibrium. I've mentioned it before. So Lindahl equilibrium is also used in these rounding techniques to get approximate core. But yeah, it exists exactly in the fractional world. And Lindahl equilibrium actually is essentially the same thing as maximizing Nash welfare. So you might have heard Nash welfare before. Nash welfare is just the product of agents' utilities and maximizing that. In particular, if we are in what's called the uncapped setting, where we can spend the entire budget on any given project, then it's the same thing as Nash. The problem is it's not the same thing as Nash anymore. If we are in the capped setting, we cannot spend all the money on a single project. However, there's something else that you can maximize, not the Nash product, but this here. So I will not be able to explain why this works, but it works. So what are the variables here? So xj is, so I'm switching into notation now from P to J. J is our project. So the amount we can spend on J is at most the cap, which is the cost of J. And then we have these Bij variables, which is how much of I's money goes towards J. So if we sum all of that up, it equals xj. How much money does each agent have? Bi. This will usually be just the budget divided by n. And then we maximize this magic function over these variables. So what is this? Like this says, agents should spend money on things that they have a high valuation for. And this is some kind of entropy term that wants the spending to be as equal as possible between voters. But yeah, so this gives the call. So I wonder whether this program or analogs can be used anywhere else in collective decision making and might have good properties. Okay, so let me quickly finish with some more practical things, because this is a tutorial. So if you want to do PB research, you must know about these things. There's something called Parbulib, the participatory budgeting library, that contains a lot of data sets, real-world election data sets. This is an amazing resource. These are large elections with thousands of voters, hundreds, sometimes hundreds, certainly dozens of projects, lots of data there, certainly the best preference data of any kind available. But in particular, it's about participatory budgeting. So they have 1,400 files from 8 countries, 21 cities, a total of 7 million votes spread out over all the years. Most of them are approval elections of various kinds, but there are also some cumulative elections. You have 10 points, spread them, and ordinal elections, as well as some completely useless files where voters were only allowed to vote for one project. And here you can see the sizes. So there are some data sets here with 150 to up to 200 projects. And there are plenty of files with between 60 and 100,000 voters. So you can simulate all kinds of things in those data sets. And how will you do that? How do you do the simulating? You can use the Pavu Tools Python package. Pip install Pavu Tools. It can parse the files that you find on Parbulib. So these are very easy to parse, a very simple format. And then you can compute your favorite voting rules on them. I believe the package is open for contributions. So if you come up with your own stuff, you have interesting things in your own papers, you can pull requests and add them to the tools. Okay, that's it. Thank you. Trying to get to the start.
Any additional questions?
Anyone? Is there a connection between this and like how you pay artists on platforms such as Spotify and Deezer? Like listening
it feels similar. The money goes to some people.
And listening to a song is approving this, and so they have different systems, the two chairs, like.
Yes. Yeah. So So there's a Spotify way where they take like 0.1% of total worldwide listening time into this artist. So 0.1% of the money that we give to artists is going to go to them. And the other obvious option would be to say, well, we have this much money, we have this many listeners, we divide it equally, and then if you spend 10% of your time listening to a particular artist, we will take 10% of your money share. That's clearly more similar to how MES does it. So there is certainly a conceptual similarity between greedy as it actually happens and equal shares that would do it differently. I think there's been a little bit of academic work, maybe by Jobst Heitzig, but I'm not sure.
I want to respond to this. There is a recent paper by Niklas Tech. They are working exactly with this model, how to fairly divide between artists. I can give you a reference.
So what happens if we allow randomization? So like my rule can now, so you have this subset of projects. So there is a distribution over this subsets and I sample, there is a rule we just samples from this distribution and pick that project as, the subset of projects as.
So you can, probably you sample over bundles of projects.
Yes, exactly. Yeah.
There's not been very much work. There's been a bit of work. I think mostly what they study is take MES deterministically, and then it spends like 50 to 70% of the budget, and then randomize over how you complete it. And that way you get ex post EJR and can try to see how much ex ante guarantees you can get with the remaining money. Though it's a bit unexciting, yes, as a method. I mentioned the fractional version. Of course, you can presumably Birkhoff von Neumann it, but I'm not actually sure with knapsacks whether this is still true.
Maybe we can say something on high probability statements. So with high probability it supports these axioms or whatever we have with some guarantee on expectation. I don't know, those kind of things.
There's probably more to be done. Yeah.
Maybe let's go to the coffee break and come back.
Thank you.
So I'm curious.
I'm done.
Because you told me that maybe
I never know in advance how long it takes.
Yeah.
I think I would get used to it.
Pas cette année, mais ça peut être l'année prochaine.